Okay, so this is the video for graphing polynomials using just derivatives. And here I have a list of everything that we're going to need to do this. We're going to need to find the potential turning points, then the intervals of increasing and decreasing, which we get from the first derivative test. Then we're going to need to find the values for the actual turning points, which we get from the original equation, seen in the top left. Then we need to find the potential points of inflection. And then from there, we need to find the intervals of concavity, which we get from the second derivative test. And then once we have those, we can see if there are actual points of inflection, and then if there are, we need to find the actual values, which we once again get from the original equation on the top left. And then we need to draw that graph using everything we've just gotten. So I'm going to make this smaller and move it out of the way a little bit. So what we first need to do is find the first derivative of this equation, and I'll explain why. So y prime equals, and this is just a power rule, 3x squared minus 3. And then from here, we set this equal to 0. And why we do that is because derivatives are defined as the equation for the slope of the tangent line among a curve. So when we set the equal to 0, we're finding the slope of the tangent line being 0. So we're finding a slope of 0, and that only happens when you have turning points, or at least potential turning points. You see here the slope is 0 at this turning point. That's what we're trying to find, turning points that have a slope of 0. So we're just going to solve this using basic algebra. And you can divide by 3 just to clear that out. And then 1 equals x squared, or you can write that as x squared equals 1. And then when you square root both sides, make sure you don't forget the plus or minus. So we get x equals plus or minus 1. So those give us our potential turning points. So let's write that in the top left. X equals 1, x equals negative 1. Potential turning points. So now we're going to use these values to determine if they're actual turning points. And to do that, we're doing something called the first derivative test. So here we have 3 zones, zone 1, zone 2, and zone 3. And this is called the first derivative test. So we're going to test each zone to see if we get a positive or negative answer when we plug in x values. So to test the first zone, we're going to need to plug in an x value less than negative 1. So let's do negative 2. And we plug these into the first derivative. So let me actually rewrite that now. Y prime equals 3x squared minus 3. So when you're doing the first derivative test, it says it in the name, first derivative, so you must use the first derivative equation. Don't use the original. That's only for finding the actual values, which we'll get to later. So if you plug in a value of negative 2, you'll see that we get 3 times negative 2 squared, which is 4. So 3 times 4 is 12 minus 3. We get a positive value there. And that's all we need to know. We don't need to know the actual value. We just need to know if it's positive or negative. So for the second zone, if you can plug in a value of 0, make sure you always do that. That just makes it very easy. So 3 times 0 squared minus 3. This all cancels out because you're multiplying by 0. So you get negative 3. So this is a negative value. And then for the third zone, you have to plug in a value greater than 1. Let's just plug in 2. So 3 times 2 squared minus 3, that's going to be positive. And that's all we need to know. We don't need to know the actual values for any of these tests here. So since this is positive, negative, positive, these are intervals of the graph increasing or decreasing. So let's write that here. Increasing, decreasing, increasing. And that's pretty easy to understand. When you're positive, you're increasing, meaning the graph is increasing in y value. If it's decreasing, it looks like that. If it's increasing again, it looks like that. And the reason why we need to test this is because if you have positive, positive, you can't have a turning point there, because if you're going positive, positive, that's not a turning point. A turning point is if you're going from positive to negative or negative to positive. So say we're going from positive to negative, this would be the turning point. Okay. So now we have just determined that these are actual turning points since the signs are switching in each zone. So the next step would be to determine the actual values for these turning points. And when I say actual values, I mean using the first original equation to find the actual y value. You don't use any of the derivatives, any of the derived equations. You just use the original equation when you're trying to find the actual value. So y equals, we're going to do this for 1 and negative 1, which are where both of the turning points are. So let's just do negative 1 first. And we get y equals negative 1 plus 3 plus 5, y equals 7. So let's write that here. Negative 1, 7. That's one of our turning points. And then we're going to plug in 1 for this. We get y equals 3. So these here are our actual turning points. And now we need to go back to here and graph the intervals of increasing and decreasing, which we actually wrote here. So the graph is increasing from negative infinity to negative 1. And here is where it gets a little tricky. You have to put a hard bracket here because it's a turning point, and at the turning point, the slope is 0. So you're going to be asked if that is positive or negative. It's both. So you're always going to include the turning points in intervals of increasing or decreasing. And this is in union with 1 hard bracket going to infinity. And that's just this side and this side are both intervals of increasing. Intervals of decreasing would be this zone, since we have a negative there. So it's negative 1 to 1, and once again, you must include these. So whenever you're in the first derivative test, you include the turning points every time in your intervals of increasing or decreasing. I'm just going to make this smaller so we can move on. Okay. So now we're going to move on to finding points of inflection. And what these are, it's basically the point where the concavity of a graph changes. So I'll draw that real quick. So you can say this is concave down, and then this is concave up. The point of inflection is the point between these two turning points. It's not always directly in between them, but it's a point within this curve here that it changes from concave down to concave up. That's what a point of inflection is. And to find that, we have to take the second derivative of this equation. So y double prime equals 6x. That's just another power rule from this equation. And we must set this equal to 0. 0 equals 6x. And you solve for x to find any potential points of inflection. So the only potential one is x equals 0. So potential points of inflection, x equals 0. And now we have to test if that is an actual point of inflection or not. And to do that, we're doing something called the second derivative test. Pretty similar to the first derivative test. This time we only have 2 zones. And we're going to do the same thing. We're going to plug in values to see if these zones are positive or negative. But since we're doing the second derivative test, we have to plug into the second derivative, not the first, not the original. So let's pick a value of -1 for the first zone. So y double prime equals 6, -1. That gives us a negative value. That's all we need to know. So negative value, and then second zone, 6 times +1, positive value. That's pretty straightforward. And what these values mean is that this is concave down, and this is concave up. And similarly to how the first derivative test worked, if these values are like going from negative to positive or positive to negative, that just allows you to know that it's an actual point of inflection. It's not a false. We're finding potential points of inflection, and since it's switching signs, it's an actual point of inflection. And that just determines that for us. So now we're going to find the intervals of concavity, which we already kind of wrote here. So the graph is concave down from values -infinity to 0. And this is actually a really important thing right here. This 0 is not included. So you put a soft bracket. And the reason why is because it's undefined there. The value at x equals 0 has an undefined slope. So it can't be included. It's not like how in the first derivative test you have a slope of 0 where it's both positive and negative. Here it's undefined, so it's neither. So you can't include it. And then concave up would be 0, once again not included, to +infinity. So now all we have to do is find the point of inflection, the actual value, which we get from plugging x equals 0 into the original equation. So point of inflection, y equals 0 cubed. 0 cubed minus 3 times 0 plus 5, y equals 5. So our point of inflection is 0, 5. And from here, we have all the information we need to actually graph this. So I'm just going to scroll down to give myself a little more room. And I'm just going to put down all of the major points we have. Make sure to label your axi. So our point of inflection is 0, 5. That's a valuable point to put down. And then our turning points, -1, 7, and 1, 3. So 1, 3, and -1, 7. So now we have all the points we need, and we just use these intervals here, the intervals of increasing and decreasing and the intervals of concavity, to actually draw the graph. So the graph is increasing from -infinity to -1. So that shows that it's increasing and it's concave down. So if it's increasing and concave down, it looks something like that. And then from -1 to 1, it's decreasing, seen here. And from -1 to 1, it goes from concave down to concave up. So it's concave down until x equals 0, and it's concave up after that. Or it's not included, but it's concave down until it reaches that. So it's concave down and decreasing right there. And then it's concave up and still decreasing right there. So you can see that this is concave down, this is concave up, and then from here, we're increasing from 1 to +infinity. And that's all you need to know. You just need to find the turning points, points of inflection, and your intervals, and you're able to graph any polynomial. All right.